Welcome to the first episode of On the Fritz.
Rechargeable lithium-ion AA batteries have been available for about 10 years, yet billions of disposable alkaline batteries are still sold every year. Why has the chemistry used in everything from smartphones to electric vehicles failed to dominate this market? To find out, we purchased and lab tested this selection of 10 brands and have some interesting data that isn't available in manufacturers' datasheets. First, some terminology. Technically, these are cells. Batteries consist of multiple connected cells. The term batteries is used to reach a broader audience. For the rest of this video, we'll call them cells. But lithium-ion AA's aren't just cells. All the tested devices have an integrated buck regulator, which converts the 3 to 4 volts of the lithium-ion cell into the 1.5 volts you'd expect from a AA. A pulse width modulator switches a MOSFET on and off at a fixed frequency and a variable duty cycle. The chop voltage from the MOSFET is smoothed down to 1.5 volts by an inductor and a capacitor. Under load, the pulse width modulator varies the duty cycle to maintain the output voltage. Under light or no load, it operates in discontinuous mode, leaving the MOSFET off until the output voltage droops. The trade-off for this complexity is a much higher efficiency than a simple linear regulator. The charging circuit of most cells is activated when voltage from an external charger is detected. Kentli cells are charged through this ring contact. It seems to be directly connected to its internal cell, judging by the power we could draw from it. Other cells have separate micro USB or USB-C interfaces for charging. The space taken up by these connectors means a smaller internal cell and less capacity, but the convenience of charging with a USB cable will be handy in some applications. To test capacity and energy, we connected the cells, devices under test in this diagram, to an electronic load that drew exactly 1 amp and logged their voltage until they were discharged. An environmental chamber maintained a constant ambient temperature. A programmable relay allowed up to 8 cells to be automatically tested, one after the other. A single-board computer running ARM Linux controlled all the instruments and gathered raw data for processing and upload to a database, where a web server presents the information. The offshore brands don't provide much technical data. To check our methodology, we ran the same discharge tests on disposable alkaline and lithium cells. The data for Duracell and Energizer cells matched up well with our results. And the clear winner, with over 2 amp hours of capacity and almost 2.9 watt hours of energy, is the Hixon J818. Hixon advertises 3.5 watt hours of energy, which at a constant 1.5 volts works out to a capacity of 2.3 amp hours. The energy we measured is less than this because we tested them with a 1 amp load to reduce test times. You can expect the capacity and energy of these cells to be significantly higher at lighter loads. Hixon doesn't provide a load charge indication. Instead, they tend to flail at the end, at least at our 1 amp test load. Jugee, Maxlithium, Maxwel, Palo, and Smartoools indicate low capacity by reducing their voltage to less than a volt. EBL cells also reduced their voltage, but only briefly. Tenavolts cells reduce their voltage through multiple steps. Only the Kentli cells mimic ordinary cells with this gentle roll-off. You can expect them to be compatible with any battery-level sensing circuitry designed for alkaline cells. Pownergy cells abruptly and decisively shut off, providing no warning to devices powered by a single cell. When a cell in a battery shuts off, it will be reverse biased by the connection to the load. All the tested cells have a drop between 0.3 volts and 0.7 volts in this state, as if they have an internal diode, which reduces the output voltage of the battery even more. The MOSFETs and buck converters generate a lot of electromagnetic interference, or EMI, that can cause mischief in sensitive equipment. To measure how much of this EMI gets out, we modified an industry-standard test for conducted EMI. As its name suggests, a line impedance stabilization network, or LISN, provides a stable, repeatable impedance to the device under test. It also isolates the connection between the spectrum analyzer and the DUT, so only EMI from the DUT is measured. A second LISN provides even more isolation from noise generated by the electronic load. The controller steps the electronic load through a range of currents and for each load current sweeps the spectrum analyzer through a range of frequencies. The test generates the data we need to provide a three-dimensional graph of EMI at various frequencies and various loads. To measure the baseline noise floor, we used an ordinary alkaline cell. All the ambient peaks were well below 20 dB microvolts. These steps along the frequency axis are caused by the spectrum analyzer switching ranges. For comparison, the peaks of an Apple 5-watt power adapter are about 20 dB or 100 times above ambient. This peak at 170 kHz is probably the fundamental of the switching frequency. Our methodology is based on an industry-standard compliance test. Such tests were written decades ago, long before real-time spectrum analyzers and Python libraries existed. They used techniques like quasi-peak averaging to pass transient emissions. Is this still the best way to characterize EMI? It's just a few calls to the NumPy library to process signals. For example, the volume below a 3D plot of amplitude versus frequency versus time might be a better metric for EMI. Let us know in the comments below what you think. In any case, it's safe to say these cells generate an exceptional amount of EMI that portable devices almost certainly aren't designed to filter out. The peaks of the quietest devices were about 30 dB above the Apple power supplies. The noisiest were almost 50 dB or 100,000 times as noisy. Sharp-eyed viewers will notice some averaging was done in these plots, while those on our website are decimated to peak values. You'll notice two distinct areas in these graphs. At lower currents, there's a low-density broadband hash, typical of discontinuous mode. At higher currents, there are hard peaks at the switching frequency and its harmonics, typical of continuous mode.
Lithium-ion cells are good replacements for disposable alkaline cells in flashlights and motorized devices like electric shavers, toothbrushes, and toys, but not in sensitive equipment like laboratory instruments, microphones, radios, or in devices with high inrush currents like photo flashes. Not all brands indicate low battery, and all suddenly drop to 0 volts when completely exhausted. They shouldn't be used where an unexpected loss of functionality is inconvenient. And finally, don't forget, there's no industry standard for chargers. You'll have to buy a proprietary charger for cells that don't have an integrated USB socket. Thanks for watching. You know what to do if you like this video. Comments and suggestions are welcome below. Our Assault on Battery scoreboard is published for all to see at the link here. We're an independent test lab, not sponsored or influenced by device manufacturers or retailers. For online access to all the web pages shown in this video, as well as future test results, please consider supporting us on Patreon.